In this series of videos I've been repairing and restoring a pair of Hazeltine 2000 smart terminals. I'm getting towards the end of the project now. This is the second of the two terminals and it is now up and running. I've carried out most of the repairs. As you can probably hear, I've got the fan fitted. I've dealt with the bearings on the fan, replaced those, so it's nice and quiet. Be even quieter once it gets the cover on. And before we finish this series, I will be coming back with a follow-up series on using this and attaching it to various devices. But before we finish this series, I just wanted to go over some of the additional repair work that needs to be carried out as part of a process like this. I normally kind of gloss over a lot of it because it's fairly dull and tedious stuff, but I have been asked about it, so I thought I'd just briefly mention it. In something like this, about 90% of the work is actually in the chassis, the metal work, the cosmetics, and just trying to make it look nice. The actual repairs, the electronics, actually only take about 10% of the time. The rest of it, as I say, is in the remaining work, which can take quite a lot of time and effort depending on how far you want to go. So things I've done on this chassis so far amount to straightening out a lot of bent parts. These machines are quite heavy and a lot of the bits that stick out are quite flimsy, so they do tend to suffer and get distorted and bent. We'll have a quick look at some of those in this video, but I've done most of the repairs on the chassis, straightened out all the bits that were bent. I've made some replacement parts, so for example the switch insert, one was missing, and it's things like this that attention to detail makes a big difference. So for example, with something as simple as an insert, the ones on these switches, the aluminium, and the way I make the insert is to get a bit of stock aluminium, put it in the lathe chuck, face it off so it's got the correct finish, turn it to diameter, so these particular ones are 9.65 millimeters, and then I part it off. So when I do that, one of the important things with these, and it's kind of hard to see, it's the face of these are slightly concave, and if you don't get that right, it won't look right. The reflections on them will look different and it will really stand out. It does stand out a little bit because it's 50 years newer than the other three, so it is a bit more it looks newer, it's slightly shinier, but it will kind of bed in quite quickly. But to get this taper, this concave finish, you can do it in two ways. You can either machine it into the shape, or what I do is when I'm parting off the disc, because what you're trying to do is really make a small disc of aluminium, is when I part it off, it's 0.4 millimeters thick, but what I do is I angle the parting tool very slightly, and what that does, it kind of spins a very slight disc shape into the finished part, but it leaves the back flat, and you end up with this nice concave finish, and it's quite consistent, so you get a very nice matching appearance, so it doesn't stand out and it looks like it's always been there. Other things, some plastic parts needed fixing on this. The cables, they weren't too bad. The end of one cable was fairly badly chafed, so I cut that off and remade the connections. Carried out a fair number of repairs to the actual chassis, mostly in terms of straightening bits out. But then we move on to the casework, and this is where the time really starts to get taken up, and we'll have a quick look at some of the parts that I need to work on or have worked on with the chassis, and this actually applies to both of the two machines I've worked on here. So one part that took quite a bit of effort was this. This is of course the front cover for the outer case, and it's a piece of perspex, but it's got a painted mask on the underside, on the inside, and unfortunately when you get these, they tend to have the double-sided, or the remnants of the double-sided foam that adhered them to the case still stuck to their back side. And the problem trying to get that off, of course, is you don't want to take the paint off, and the tape seems to be stuck to the paint better than the paint is stuck to the plastic, so It is a bit of a challenge getting that off without damaging the paintwork, but I got all that off. That took about 2 or 3 hours on this particular part because the foam was extremely hard and it had completely set into a solid lump, and it was all the way around and across the section on the right. So that took quite a bit of effort. Once I've got that off, I polished both sides with Novus number 2 plastic polish. Try and remove all these scratches. So I'm trying to get a nice finish here so there are no scratches visible, and also it's nice and clean. Then I give it a good wash, final polish, and that part is now done. We then get parts like this. This is of course the surround for the CRT. This was in quite a poor state when the machine arrived, had the remnants of the thick foam around the outside, but more importantly one corner was completely broken, so it was just flapping about. There are lots of ways you can go about repairing these, of course. What I did in this case was make up some small inserts, and the idea with these is they sit, there's one in each of the 2 corners, although only one corner was broken. I did the 2 bottom corners, but these sit inside the frame like this, and then they get bonded into place and it stiffens up the corner. They don't get in the way of anything, but they make the entire frame much stronger, and as I say, you can't see it from the outside once you fit this back onto the machine. Spent some time cleaning it up, getting all the residue and the dirt off it, and it's come up quite nicely. This is inside the machine, so you can't really see it that well, but even so it's nice to get this clean, and then if the owner wants to, he can refit some foam to it. There's normally a fairly thick strip of foam around the outside of this, and it kind of seals the face of the CRT to the inside of the outer case. Okay, so that's now done. As with the first machine, I spent quite some time cleaning up the outer case. You can see I haven't straightened this one out, it's still fairly badly bent up. The flap won't open and close properly, so it's better than the first one, but still needs quite a bit of work. This is caused because this entire front section is bent, and I suspect at some point, although this had screws in when it arrived here, I suspect at some point it's been shipped without the fixing screws in place. You can see where the inner chassis, which is very heavy, has been impacting it at the corners. So I'll need to straighten that out. I'll need to straighten the door, redo the pivots, probably replace the spring, straighten the front out, straighten the entire case out, and once I've done that I can refit the front insert. So it's quite a lot of work in this. It'll probably take an hour, hour and a half, 2 hours to do that. Depends on how badly bent up the case is. The main difficulty of course is I don't want to have to refinish this, so I need to try and straighten this out without taking the paint off, and that's always a major challenge. Also, it's aluminium, and almost certainly this front section will have stretched, so this you can't just easily straighten it out because there's now, if you like, too much length of metal between this point and the corner. So if you just try and flatten it out, you'll close this gap up and then the flat won't fit. So that's always a bit of a challenge, but once it's done it does make the whole machine look much better, and it is worth spending time doing this. It does make the final product so much nicer to use and so much nicer to look at. So that's what I'm going to do next. I'll get this into the workshop, get this straightened out, get back on camera, have a look at the finished result, and we'll then move on and have a look inside the keyboard. That's the outer case pretty much sorted out. I've straightened it out as much as I can. It's not perfect, but it's certainly a lot better than it was. The flap now opens and closes the way it should, and the spring, I didn't need to replace the spring on this one. It did need to be kind of retension, but it's still the original spring. What I can do now is use some double-sided foam to reattach the front panel. So my original plan was to leave the front panel off and strap it to the top to ship it back to the owner, but unfortunately because the case tapers out, it's wider at the bottom than the top of the case, so I can't do that. So I do need to fit it back into the outer case and hope it survives the trip back. So I'll get the front panel reattached. We'll have a look at it, see how it appears, and then that should be the outer case completed. I've got the tape fitted to the front of the enclosure. I can peel the backing off now and reapply the front infill panel. That's the front panel refitted, and hopefully you can see the case does now look very much better. The front flap works, the front infill's nice and clean, it's nice and clear. I've got rid of all the scratches on it. The back of the case also looks to be in good condition. I had to straighten out some of these fins, they were bent. So this outer cover is now ready to refit to the machine, and the next thing we need to turn our attention to is the keyboard. So I'll get this out of the way, we'll get the keyboard onto the bench and see what's inside that. This is the keyboard off the second unit. I haven't tested this yet other than the normal static test looking for shorts, and I've given it a good clean. As you can see, these do tend to get very dirty inside, and it's come up quite nicely. It's got a date of 1973 stamped on the inside. The rest of it looks to be in fairly good condition. The only thing that's missing off this is one of the lens caps. Unfortunately, that's going to be quite difficult to track one of those down, but the rest of it seems to be in fairly good condition. I've tested the operation of the switches. The on-off switch is a little bit dirty still. It needs cleaning, needs the contacts cleaning, but the rest of it seems to be fine. The lead on these is very thick, so there are quite a few conductors in this lead, but this one seems to be okay, so hopefully all the connections will be fine. So the case looks fine, so we'll look at the inner workings of the keyboard. So this is the PCB assembly from inside the keyboard. As you can see, fairly standard layout, but it is quite an interesting keyboard, so we'll have a quick look at this and I'll explain how the keys actually work on this. First thing is, this has a different type of device than the first unit, and it's a fairly common, it hasn't got the actual manufacturer's part number on it. It just says ROM 0011, which is the Hazeltine part designation for this, but it's not really a ROM. This is a keyboard encoder controller, and this is one of these instances where a bit of experience really helps in tracking something down. I've seen this type of device quite a few times, so once I'd seen the pseudo schematic for this, I'll have a quick look at that. So you probably won't be able to see this very well, but we've got this device in the center here. That's this what's called a ROM in this on this board, but it's actually, I believe, an AY52376. I'll come back to why I think that's the case in a few minutes. But it's an interesting device. It contains a lot of the scan and detection circuitry for making a keyboard control matrix. So it has a clock input that creates some scanned outputs, and then there are some scanned inputs, and by scanned inputs what I mean is there are some internal counters, some internal comparators, and what the device does is at each step it checks to see if the output of the comparators matches the current count on the counter, and if there's an active output then it decides a key has been pressed, and it can tell which one's been pressed by the count on the scan outputs and the count on the scanned inputs, and then it activates an output code based on the current input value. So it's kind of like an automatic ROM lookup system, and there are some discrete keys here, so these are the function keys that are not part of the scanned matrix. There's a table down here that shows what the scan codes are for each given output. But the reason I think this is the AY52376 is if you look at the spec sheet for that device, you'll notice that all the input pins match the pins shown on the schematic. They're not numbered here, so we don't really know which one's which pin, but looking at the designations, almost certainly it's this device or a derivative of this device. Either way, this is the internal architecture for it, and we have the ROM itself, we have the comparator and counter, and then we have the output driver, and then we have the output driver, which is really nothing more than a ring counter. So this drives the output here, these drive these outputs, which are the output from the ROM, and then there is this short delay, and this just allows setup time for the output to be stable before it actually sets the strobe output, which is used to tell the system somebody's pressed a key. So it's quite straightforward. What's unusual about this keyboard is it shows on this spec sheet that there's a kind of a typical switch, it calls it here, which is normally mechanical switch. But this keyboard does not use mechanical switches. It uses a capacitive system. So there are a couple of tracks underneath each key that are not connected to each other. One track has a 100 kilohertz signal applied to it, and the other track is attached to a transistor that goes to the input of the encoder. Now, it tends to work really well. The only problem with this, and it's fairly immune to kind of dust and dirt to a certain extent, and there are no contacts to wear out. The real problem is that the transistor for each key is underneath these metal housings, and firstly they're all riveted together, so you can't remove one at a time, and also there are about 100 of these little twist tabs that you have to undo to get the keys off. The keys are not reattached to the board other than by this mechanical attachment system, and then they're just sprung-loaded plungers, so it makes it very reliable. The only pain is if one of those transistors fails, it's a real pain to try and change it, because you have to remove the entire mechanical assembly. That said, these keyboards do tend to be fairly reliable. I haven't tested this one yet, so I hope I haven't just shot myself in the foot by saying that. But what we'll do before we go any further is I'll just demonstrate the principle for these keys. As I said, they're quite interesting, and it might make more sense if I just do a quick demonstration as to how this technology works. What I have on the breadboard here is a representation for a single circuit for one key on the keyboard. Each of the keys has a similar circuit, and this is the schematic for it. It's based around a single transistor. This is the one that's hidden underneath each key, and the transistor is controlled, its base is controlled by being capacitively coupled to a 100 kilohertz square wave signal, or it's not coupled to anything. So if you press the key, it couples it capacitively to this signal. If you release the key, or no keys are pressed, the input to the transistor is effectively floating, but in reality it's pulled low by the input to the IC, that's the control IC. So this resistor inside this dotted square box is really the input load represented by the IC itself. And the output is a filtered version of the 100 kilohertz square wave. So if you press a key, that signal is fed through to the transistor, turns the transistor on and off, and that is filtered by the capacitor down here. And effectively what we're doing here is filtering the output that goes through to the this is the input to that IC, and it's used to select which particular ROM value is fed out onto the data bus. So it's very straightforward. That's what I've got set up, and we have the input signal applied to this green wire. It's not connected to anything apart from the input signal, so it's not connected through to the transistor at all. We have the orange wire, which again is not connected to the input signal. The two just run fairly close together here, kind of similar arrangement to what we have on the keyboard. And what I have here is a key plunger. It's actually just a washer, of course, on a piece of plastic, but this is how the keyboard's arranged. There's a metal disc at the bottom of each key plunger. There's a spring. When you press the key, it pushes down the metal plate and brings it into close proximity of the conductors on the PCB that are formed through the tracks on the PCB. On the scope we have the blue trace, which is the output of the signal generator. I'm using my Juntech PSG 9080 here, and it's feeding in this case a 1 megahertz pulse through to the input wire, which is the green wire, and that's the blue trace. The yellow trace is the output from the transistor. Now there's of course no scaling, there's no real control on this, so normally you'd have this connected to the input of the encoder, which has SMIC triggers, that sort of thing, to condition the signal going into it. But in this case we should still see that there is a response when I bring our key plunger close to the conductors. And you can see that the yellow trace, I'm not touching, so this is not electrically coming into contact with anything here. This is just purely capacitively coupling these two wires together, and you can see that that effectively turns on the circuit, the output goes low, and we effectively have a key press. And there's no mechanical switch to wear out, and it of course means that in theory the keyboard can be very reliable. It's almost immune to dirt, you can't get dirt on the contacts. If you get too much built up in there, then you will get problems because it will think the key's pressed all the time, because the dirt will effectively form a capacitor. So you can see it works very well, very reliable, and it's quite a nice system, and that's how this keyboard works. So what I'm going to do now is go away, finish testing the keyboard, finish cleaning it, I'll get it reassembled and tested, and then in the next video we'll have a final look at that second Hazeltine 2000. Once that's done, I'm going to put the CRT back into the first unit, and then we can start having a bit of fun with it and testing some of the more advanced features.